The next part of our kinetics chapter deals with reaction mechanisms, looking at a rate law. Rate is equal to K times the concentration of our reactants raised to some order, and using that information to try to develop an understanding of the pathway in which the reactants took to reach the products. The process by which a reaction occurs is typically called a reaction mechanism, a multi-step process in which reactants collide to turn into a product. A reaction mechanism is a pathway. Each one of those elementary reactions, when added up, will create the overall equation we're used to seeing, left equals the right. However, there is an activation energy for each of the elementary steps along the way. And remember, it's the activation energy, that energy barrier between the reactants and products, that determines the K, the rate constant. And according to Arrhenius, we know that that rate constant is temperature dependent, that the frequency factor raised to negative EA over RT, where EA stands for our activation energy, the barrier between reactants and products. R is the gas constant in the metric unit 8.31, and T is the Kelvin temperature. So the rate constant varies with the increasing or decreasing temperature. As we look at a pathway as reactants turn to products, we get great insight when we look at the activation energy curve. Let's suppose we have energy on an XY axis, and I'll just label on the y-axis this is energy, typically measured in joules, and on the x-axis is time going by. As time goes by, reactants turn to products. Let's suppose we look at an energy graph in which we see three different energy barriers. So here will be the initial reactants. We'll just start them at about this level on our XY axes. And I see the first energy barrier, and then it comes back down. Then I climb a next energy barrier, and it comes back down. And then a third energy barrier, and it finally reaches the end in which we have our products. I count 1, 2, 3 different energy barriers. This is giving me insight into the reaction mechanism. This must have occurred in 3 elementary steps. When reactants turned to products, it took 3 different collisions with the reactants forming intermediates along the way. In this first energy barrier, we could list from the beginning of the reactants to the top of that hill, the activation energy for our reaction 1. This would have a value known as K1, the rate constant for the first elementary reaction. From the reactants all the way to the top of the second energy barrier, we would have the activation energy for the second elementary step, and this would have a rate constant known as K2. And again, in the third elementary step, all the way back down to the reactants, we would have a third value of the activation energy and a third K value for that third elementary step. When I look at this particular energy graph, reactants form products over time. It looks like that it took 1, 2, 3 different collisions, 3 different elementary steps for the reactants to finally achieve the overall product. Each time we have a collision in an elementary reaction, we produce something known as an intermediate. An intermediate is something that is made by a collision but then gets used up in the next step. An intermediate gets made but then immediately used. So we're looking at a reaction mechanism really as the pathway that reactions follow to achieve reactant-product overall equations. It's a series of steps that actually occur in a reaction. Kinetics tells us a whole lot about the mechanism. Understanding the elementary steps allow us to predict reaction pathways. Oftentimes when we see a balanced equation, it doesn't tell us how the reactants became products. For instance, in this equation, we have 2 molecules of NO2 combining with a molecule of F2. 1, 2, 3 total molecules on the left. And I see on the product side, they've rearranged to form 2 molecules of NO2F. If I look at this particular reaction, just visually for a moment, a molecule of NO2 could be represented with this figure. A second molecule of NO2, and finally the F2. There are 3 molecules on the left side of our equation. How do they achieve the overall product, 2 units of NO2F? Do all 3 of them collide together and magically turn to the product? Do I have 1 molecule of NO2 colliding with an F2? Do I have both of these molecules colliding together and then in the next step collide here? What we're trying to do is predict, looking at the number of collisions, how can we use kinetics to give us insight into the order in which these molecules collide to give us the desired product? If I were to look at 2 NO2F and F2 and the way that they collide step by step, we would develop what's known as the reaction mechanism. If this rate law that is observed shows rate is equal to K times NO2 to the first order and F2 to the first order, that rate law gives us great insight into what's actually colliding. Notice that the stoichiometry does not give a role, but what it's giving us insight to is what's actually colliding. By looking at this rate law, I would predict that a molecule of NO2F in a first elementary reaction has to collide with a molecule of fluorine. There is my first collision. Remember, at the top of the activation energy, we get this intermediate. At the top of the barrier is an intermediate. That's where bonds are breaking and new bonds are forming. We're rearranging to produce an intermediate. Suppose with that first collision, NO2, 1 molecule here, collides with an F2 and they produce NO2F. So in other words, I'm going to take off a fluorine and NO2F would now be breaking its bonds, and what we've got is an intermediate. So just by thinking through what's happened, this would be sitting on top of that energy barrier up at the top of the hill. This isn't a product, and yet it is made in that first elementary step. If I look at the next step, this fluorine atom then collides with the second unit of NO2, giving us our next product. So again, if I break the bond, snapping on the next fluorine, we now see on the product side 2 molecules of NO2F. It happened in a 2-step collision, where the first step, the slowest step, came directly from the rate law. In a faster step, which just means it had lower activation energy, the product then was formed with a second unit of NO2F. Thinking about this energy diagram, if the first collision was the slowest, I had at the top of the larger activation energy hill, and then I had a smaller hill before I finally reached a product. Thinking through, just by looking at the rate law comes from the slowest step, the one with the largest activation energy. This would give me what's known as K1. And in that faster step, a smaller amount of activation energy would give us what's known as K2, a 2-step collision in order to get the reactants to turn to product. Thinking about what we started with, the reactants, we had NO2, another molecule of NO2, and a molecule of F2. We decided the first collision based upon the rate law would be a collision of the molecule NO2 with a molecule of F2. And at the top of that barrier, we formed what was an intermediate. The intermediate was that single molecule of fluorine. We already produced one of our products, NO2F, but at the top of that energy barrier was that atom of fluorine. Notice immediately in the next collision, it hit with the second molecule of NO2F. Immediately made, but immediately used in the next step, we call this fluorine atom an intermediate. Something that's made and then used up in the next step doesn't appear in the overall equation because they cancel. The right side would simplify with the left. F is called an intermediate. It is formed, then consumed in the reaction. Our intermediate that was produced was a fluorine atom as a result of our first collision. And that first collision produced a molecule of our product, but left us with a fluorine atom that then went on to hit with the second molecule of NO2. Each of these two steps is called an elementary step. The rate of the reaction can be written from its molecularity. In other words, how many molecules are actually colliding determines its molecularity. Molecularity, checking its spelling. So the molecularity is a term used to describe the number of pieces that must combine together. If I have something known as a unimolecular step, unimolecular, uni meaning one, what it's involving then is a single molecule just rearranging itself. Not necessarily a collision because it's just a single molecule, but if I rearrange bonds, I could have a unimolecular description. In a bimolecular reaction, it requires two molecules to collide. The rate is second order overall. That would have been the description up above with our first example. First order with respect to NO2, first order with respect to F2, second order overall. A second order rate shows two things colliding together. In a termolecular equation, would require three molecules and the rate is third order. However, be very cautious if you're predicting a reaction mechanism in which three molecules must collide with just enough energy and the correct orientation. It's just that the chances are crazy high. It says termolecular steps are almost never heard of because the chances of three molecules coming into contact at the same time are minuscule. When we're proposing rate mechanisms, stick to unimolecular and bimolecular. Unimolecular is a single molecule rearranging itself. Bimolecular is when a molecule of one thing, second molecule of a new thing collide together, giving us a bimolecular. That's very readily available. But if I want to predict a termolecular, three things colliding, I think it's not going to happen. It's just unheard of that chances of three things being successful in colliding is minuscule. Let's turn the page over and take a look at elementary reactions. It says they're significant and in a very important way. If we know that a reaction is elementary, then we know it's a rate law. Each elementary reaction comes directly from a collision, and therefore each elementary reaction has its own rate law. When we look at an overall equation, one that's not based on little elementary steps but many combined together, then we don't know its rate law based on looking. So suppose if I have a product called A, if rate is equal to K times the concentration of A to the first order, we know it's unimolecular. If A collides with the second molecule of A, we would know it's second order. It would be bimolecular, two atoms of A colliding together. Often written instead of A plus A, you could write that as 2 units of A, still a second order. What if we have two different molecules colliding? A collides with B, first order with respect to A, first order with respect to B, but second order overall, it would be considered bimolecular. Then I get into the world that I would not use. I would not predict pathways that involve termolecular collisions. If 2 units of A collide with B, we get third order overall. I would not predict that to be an elementary reaction. Same is true for the rest of those examples. If I'm predicting 3 molecules simultaneously collide with just the right orientation, I would not use that as an elementary, but instead predict these to be overall equations in which the pathway has been added together. So let's take a practice. It's been proposed that the conversion of ozone gas into oxygen gas proceeds by a two-step mechanism. In the first step, one molecule of ozone breaks down into an oxygen molecule and an oxygen atom. The second molecule of ozone, O3, then collides with that oxygen atom to produce 2 units of O2. Let's take a look at the molecularity for each of the elementary reactions, elementary reaction 1 and elementary reaction 2. In the first elementary reaction, we had a single molecule of ozone just reorganizing itself to create an oxygen molecule and an oxygen atom. It is a unimolecular elementary reaction, a single molecule rearranging. In the second elementary reaction, we had that ozone molecule hitting the oxygen atom that was formed above. That collision between two atoms would give us a bimolecular elementary equation. If we're thinking about the sum of those equations together, we would get the overall reaction. Adding together elementary reaction 1 and elementary reaction 2, simplifying anything that might cancel from the right and the left. And as we simplify, we notice that the oxygen atom formed in the first reaction is then canceled with the second equation, giving us the oxygen atom as our intermediate. The oxygen atom is written as O. The overall equation is simply adding together things on the left and the right, canceling out those intermediates. On the left side, I'm counting 2 molecules of ozone, O3. And finally, on the right side, I have 1, 2, 3 molecules of oxygen, O2. In a two-step process, gave us the overall equation. 2 units of ozone form 3 units of the oxygen molecule, O2, giving us an intermediate of an oxygen atom. A two-step process for this conversion. In the following reaction, if it occurs in a single elementary reaction, predict the rate law, knowing that if we call this an elementary reaction, the rate law comes directly from the stoichiometry. So rate would be equal to K times the concentration of H2 to the first order and bromine to the first order. Those coefficients are both 1s. This seems like a very plausible reaction, a bimolecular intermediates, a bimolecular, let me write that, is certainly something I would consider plausible for a mechanism. So this equation would make sense to be called an elementary reaction. However, let's consider this reaction. 2 molecules of NO plus a Br2 give us 2 NOBRs. If this is a single elementary reaction, the rate law would come directly from the equation. It would look like rate is equal to K times the concentration of NO to the second order times the concentration of Br2 to the first order. It would be a third order overall, a termolecular mechanism. Do you believe that to be a likely mechanism to have 3 molecules simultaneously collide with the correct orientation, just the correct energy? I don't think so. So no, this is not a likely single-step mechanism. Remember, the multi-steps are much more likely that this would not occur. I would then decide in a multi-step mechanism what would be an option. Perhaps the 2 molecules of NO collide, followed by a second collision with bromine. Perhaps a bromine will collide with NO, followed by a second collision with that NO. I know for sure it involves at least more than 1 step. No way would this be a single-step mechanism giving us a termolecular collision. Let's pause before we turn the page. Most chemical reactions occur by mechanisms that involve two or more elementary reactions. So each step, each elementary step, has its own rate constant and its own activation energy, as diagrammed in the charts from before. An overall process might be multi-steps where the largest energy curve gives us the rate determining step. The slowest step of all gives us the rate determining step. So that overall reaction rate cannot go any faster than the slowest elementary step. This is what's termed as the rate determining step. The overall reaction can only proceed as fast as the slowest step in the multi-step reaction. So we look at the activation energy and find the largest value to determine that slowest step. If it's a multi-step reaction, each one of those elementary reactions has its own rate law, and the rate law is governed by the slowest step. So that rate determining step governs the rate law for the overall reaction. Let's take a look at a first example in which we'll write an equation with the slowest first step. In other words, the diagram would show the activation energy for the first step to be larger than the second step. The rate determining step gives us the overall equation, rate determination. Let's suppose we have a first collision between a molecule of nitrogen dioxide with a second molecule of nitrogen dioxide. It will form an NO3 molecule and an NO molecule. And I'm going to write in parentheses that this is the slow step, indicating that it has the largest activation energy, K1. I'll place the K1 on the arrow to show that its rate constant is coming from that first energy barrier. In a second step proposed mechanism, let's take that molecule of NO3 that was formed above and collide it with a molecule of CO, a second reactant. It would have its own rate constant, I'll call K2. And in this collision, we produce a molecule of NO2 and a molecule of CO2. And I'll put in parentheses that this is the faster of those two steps, represented by a lower activation energy in the second step, K2. I'm proposing a mechanism, a two-step mechanism in which the first step is the slowest and therefore determines the overall rate. The second step occurs much faster due to a lower activation energy. If I sum together the overall equation, canceling any intermediates, I have a molecule of NO2 and a molecule of NO2, one on the left, one on the right. I have a second molecule of NO2, so I could simplify one of them, but it looks like I'll be left overall. NO3, NO3, and that looks like it. So it looks like an overall equation, NO2 plus CO produces NO from the first elementary and carbon dioxide from the second elementary reaction. We get the observed rate law from that first initial step. With this particular pattern, let's label the following words. An intermediate is something that is produced and then immediately used up. NO3 was formed in the first step and then consumed in the second step. NO3 is known as an intermediate. Now, when I look at my overall rate law, it comes from the slowest step. When I look at rate is equal to K, the nitrogen dioxide molecule, NO2, collided with itself in my first proposed elementary reaction. NO2 colliding with a molecule of NO2 gives me a bimolecular elementary reaction showing a second order with respect to NO2. Notice the other reactant, CO, does not even appear in the rate law. Even though it's in the overall equation, it was not part of my first elementary step. The observed rate law for a reaction comes from the slowest elementary step from your proposed mechanism. When I proposed NO2 colliding with a molecule of NO2, I'm proposing a bimolecular rate law with respect to that reactant NO2. Practicing with the decomposition example, let's read this. It says the decomposition of nitrous oxide, N2O, is believed to occur by a two-step mechanism. In the first step, I see that it's slow. In the second step, I see that it's fast. Visually, that's telling me that my first proposed mechanism for that elementary reaction has the higher of the two activation energies. The slowest step determines the rate law. The overall equation is found just by simplifying any intermediates that were formed and then used up. I'm noticing that O was produced in the first elementary and then used in the second elementary reaction. Looks like that's all I'm seeing that can simplify. On the left, I have two molecules of N2O forming, two molecules of nitrogen, and a single oxygen molecule. Two N2Os produces two N2s plus an O2. The overall rate law for the equation above that we just wrote comes from the slowest step. This equation can only occur as fast as the slowest step in our mechanism. Our proposed reaction mechanism would give us an observed rate law, rate is equal to K, times the concentration of N2O to the first order with respect to N2O. This would be a unimolecular elementary reaction. When a single molecule of N2O rearranges itself to produce nitrogen and oxygen, that's coming from that first activation energy, the larger of the two. If it's a single molecule rearranging itself, we called it a unimolecular reaction mechanism. The rate law comes from that slowest first step. Suppose now, in a second example here, we have a mechanism with a fast initial step. In other words, the slow step comes later on in a multi-step process. It's very difficult to derive the rate law for a mechanism in which an intermediate reactant is in the rate determining step. We are not allowed to put intermediates into an overall observed rate law. We have to express intermediates in terms of reactants only. Let me model with this example. If two molecules of NO react with a molecule of Br2 to form 2 units of NOBr, the overall rate law shows rate is equal to K, second order with respect to NO, first order with respect to Br2. Now right away I notice that if this were the single elementary reaction, we would be proposing a termolecular elementary step. We realize that 3 molecules colliding in space with just the right orientation, with just the right energy, is not going to happen. Therefore, I know that this observed rate law is coming from what we would call a fast initial step. And what we're doing now is relating an intermediate in terms of an initial reactant. How could this happen, it asks. Let's predict a reaction mechanism for this rate law. What we have are 2 molecules of NO2 and a single molecule of Br2. Do we believe that a single molecule, let's just try to get those where I have 2 NOs. Perhaps this could be an NO, and I'll get this one off. This could be another molecule of NO, and then here would be the molecule of Br2. Okay, so I don't really need all these extra bonds. Alrighty, so 2 molecules of NO and a molecule of Br2. We have to propose a mechanism to get these to our product side, 2 molecules of NOBr. We have to decide, first of all, that we agree that all 3 aren't going to collide. It's just the right orientation to go directly to product. A 3-molecule collision is not likely. So, a couple of things. Do we want to propose, as in this first step, one possibility is that an NO-NO-Br2, all three collide, bam, and then we say not likely. That term molecular equation is not a likely choice. So I'll just record that. Term molecular is not likely. So we're eliminating that choice. NO plus Br2 will not be an elementary step. So again, if we just flip the page of our notes, let's propose a second alternative mechanism. Instead of one step where all three collide, what might be a different pathway? A couple of options to consider. Suppose I take an NO and a Br and collide that. Or the other choice would be take the two like molecules and collide that. It really doesn't matter what you propose because we'll make an intermediate and then use it up in the next step. So we've got three molecules. Let's propose in a first collision that I take a molecule of NO and collide it with a molecule of Br2. In an NO and a Br2 collide, that's a bimolecular elementary reaction that's very likely. So I'm all right here. And yet I know that I need to produce an intermediate. If NO and Br2 collide, let's just put them together and get an NO-Br2. All right, so we'll have a molecule form where they're all connected together. And again, that mechanism that I'm proposing is not the observed rate law, so I know it cannot be the slowest step. It must be a fast step. Just thinking that through, it's the next step that's going to have a larger activation energy. Because see, if the observed rate law was NO to the first order and Br2 to the first order, then I know the observed rate law would come from that slowest first step. But it's not telling me that. The rate law was second order with respect to NO and first order with respect to bromine. This is not the observed rate law, so this cannot be the slow step. It must be the faster of the two steps with a lower activation energy. So now I have this product, this first product, NO-Br2. That's not appearing in the overall equation, so I know that it needs to be used up. It needs to be an intermediate. We have that second molecule of NO that needs to collide as well. In my next collision of my proposed mechanism, I'll take that unused NO-Br2 produced here and now use it up here, collide it with that unused NO molecule from the original three molecules, and go on to form 2 units of NO-Br2, NO-Br. Remember the overall equation we were trying to form just from the previous page? 2 NOs plus Br2 give us 2 units of NO-Br. I made an intermediate, used it up immediately. I proposed a mechanism that had a slow second step. Now, if this is the rate determining step, which it is, it has the highest activation energy, here's what we're now determining. That the overall equation comes, the overall rate law comes from the slowest step. This is what it would look like. Rate is equal to K times the concentration of NO-Br2 times the concentration of NO. Both first order, this would be a bimolecular elementary reaction. The problem is we are not allowed to have an intermediate in our equation. It's too difficult to measure concentrations of intermediates. I mean, because as soon as they're made, they get consumed. How are we going to measure the molarity of something like that? So the NO-Br2 is an intermediate, and we're not allowed to express rate laws with an intermediate. But no big deal. What we'll go back to do is talk about the elementary reactions above. Knowing that K1, this rate law from that first elementary reaction, and K2 come from those elementary reactions. Here's what we're just thinking this through. If I have a fast first step, NO plus Br2 are going to collide very quickly and produce NOBr2. This starts to accumulate faster than it can get used. And when it starts to accumulate, just like a bottleneck, I'm making step one goes fast, 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 but it's got nowhere to go, and eventually this concentration begins to rise. What then happens is an equilibrium is established. NOBr2 will go back to the original product. And what happens is we call that a K-1, the equilibrium of our first elementary reaction. So in the fast first step, when we start to accumulate product faster than it can get consumed in the next reaction, we make that assumption that an equilibrium is forming. And with that equilibrium happening, it just reads for us, step one, both forward and reverse are occurring very rapidly with respect to step two. We begin to create what's known as a dynamic equilibrium. Their rates are equal. So just thinking that through, K1, the forward reaction, would have a rate law that looks like NO, parenthesis, BR, parenthesis, both first order. So rate is equal to K times the concentration of NO, first order, and Br2, first order. This is the forward direction. And since their rates are equal, I'll set that equal to K-1, the opposite direction. And now what we have is NOBr2, again, first order with respect to the reverse reaction. So I'm simply looking at it from right to left. The forward reaction has its own rate law. Rate is equal to K times NO with respect as first order as well as Br2. In dynamic equilibrium, the forward and reverse reaction are occurring at the same rate. We have that set equal to the reverse reaction's rate law, K-1 NOBr2. So we've set the rate of the forward reaction equal to the rate of the reverse reaction. Remember this, what our ultimate goal is to express this rate law, NOBr2, that intermediate, we want to sub in an initial reactant. What is NOBr2 equivalent to, so I can sub it out in terms of an initial reactant? It's just a little algebra game. If I have K1 times the concentration of NO times the concentration of Br2 set equal to K-1 NOBr2, I want to solve for NOBr2 in terms of the initial reactant so I can sub that into this observed rate law. So let's just divide both sides by K-1. So that simplifies. And the concentration of NOBr2 is the same as saying NO, first order, Br2, first order. Taking these concentrations and subbing them in to that intermediate, this is what we'll get. Subbing that relationship in, and this was my algebra right here, I solved for NOBr2. If I sub in the initial thing we solved for, remember how we started, rate is equal to K times the intermediate NOBr2 times the concentration of NO. That's just taking our slowest step and writing that as its rate determining step. The rate determines from the slow step. So that's just rewriting this down here. We want to get rid of this NOBr2 because it's an intermediate. The process we used was subbing in what is the equivalent value for NOBr2 in terms of the original reactants. I'll write that here. Rate is equal to K, and instead of writing NOBr2, we'll write what we solved for, NO and Br2. And remember, we still have another bracket over here of NO, so I'll just make that with second order with respect to NO. This, my friends, does indeed match the observed rate law from this particular equation. We knew that a termolecular collision was not likely. We were trying to develop a reaction mechanism that got us second order with respect to NO, first order with respect to Br2, but using a multi-step mechanism. When I realize the overall rate law, the observed rate law is term molecular, I know the first step cannot be the slowest step. The slowest step gives me the rate law. That's not the observed rate law from that proposed mechanism. So I chose to make the first step faster and the second step slower, then simply subbing in the equivalent values for the intermediate. So in general, whenever a fast step precedes a slow step, we solve for the concentration of the intermediate by simply assuming that the equilibrium is established in that fast step. In other words, just think of this as an equal sign. Forward and reverse are an equal value. I write the rate law for the forward, set it equal to the rate law for the reverse, pulling out the NOBR2 intermediate and seeing what it's equal to. Let's take a peek at a next example. Show that the following mechanism for the reaction 2 NOs plus Br2 yields 2 NOBr also produces a rate law consistent with the experimentally observed one. So let's take a peek. The experimentally observed rate law, we just worked this. Rate is equal to K times the concentration of NO second order, Br2 to the first order. That's just borrowing that same example up above. Do you remember we had a choice to make? We had 3 overall molecules. We had molecule of Br2 and a molecule of NO and a molecule of NO. We realized that all 3 won't collide at once. It could not be a termolecular. We had a choice to make. Do I want to hit NO and Br2 in my first mechanism? That's what we did first. But another equally lovely choice was to just collide the like molecules in the first step and use the bromine in the next step. That's what this proposition of a mechanism looks like. So we're trying the alternate pathway. Either way is going to get us to the same place. So a second proposed mechanism says, let's take the like molecules and collide those. Then in the next step, take that intermediate and bombard it with the bromine, so that each one of these steps would be a bimolecular elementary reaction. When I look at my proposed step, NO plus NO is a bimolecular collision. It does not give me the observed rate law, so I know that that has to be a fast step. The observed rate law would match if it were a slow step. In the next step, that intermediate that was produced then gets consumed by hitting it with that third molecule of bromine. 2 units of NOBr would be the slow step. The rate law comes from the slowest step, so this is what we know so far in our observed rate law. Rate is equal to K times the concentration of N2O2 times the concentration of Br2. The observed rate law comes from the slow step. The problem is N2O2 is an intermediate, and we're not allowed to have an intermediate in an observed rate law. We need to sub in some equivalent value for the intermediate N2O2. We go back to that first step. Here's what we know. That the forward reaction K1 times the concentration of NO and it's colliding with itself, so that would be a second order with respect to NO. That's equal to the reverse reaction in a dynamic equilibrium, which gives the K -1 times the concentration of N2O2. And that's with first order with respect to the N2O2. I want to know what can I place in as an equivalent value for this intermediate in terms of the original reactants. So I can see to get this by itself, it's a simple division of the K constants. That in other words, N2O2 can be equal to NO to the second power. So this right here simplifies the equation of the N2O2. So let's just rewrite what we figured out. Rate is equal to K, and now instead of writing N2O2, let's sub in the equivalent amount of the initial reactants, NO to the second order, and we still have that Br2 from the slow step, which is all right to have there because it is in the observed rate law. Notice that this pathway also matches the observed rate law. Friends, we decided it wouldn't matter. We've got the same place. If these three molecules have to go and collide somehow, we get the same answer if we choose to collide two like molecules and then a second collision. Or, as in the first job, we took a like molecule of NO and Br2, collided that, and then used the third one. So both pathways got us the same observed rate law. Try this. The first step of a mechanism involving the reaction of bromine is this. Bromine molecule forms two bromine atoms. It says it's fast. It's in equilibrium. What is the expression relating the concentration of Br to that of Br2? Here's what we know. The forward reaction would have rate is equal to K times the concentration of Br2. That would be equal to K negative 1, where the atom of bromine would be second order with respect to Br. We're being asked to get the atom of Br by itself. Alrighty. So again, don't let those K's bother you. They're just going to cancel with each other. So just kind of ignore those and think about the concentrations. If a molecule of Br2 is equal to an atom of Br to the second power, we want to get Br by itself. So to both sides, to get rid of the square, I'm going to take the square root. So here's what we've just done. The square root of the concentration of Br2 is equal to the concentration of Br. We've gotten rid of the squared by simply taking the square root of both sides. However, you really don't see a square root in a rate law, so instead of that, you see that raised to the 1/2 power. Br2 to the 1/2 is how we see a square root written, is equal to the atom's concentration of bromine. So with this example, we were just looking at simplifying algebraically. If we have orders with respect to the intermediates, we'll take care of that by taking the square root if need be. So this would have the overall reaction, Br2 raised to the 1/2 power, as the equivalent of that intermediate, the bromine atoms. Let's pause there for a moment. The last topic in our note pack relates to catalysts. Catalysts are those things we add to a reaction to speed them up. Not a reactant, not a product. They're there to alter the pathway. Nature has enzymes as biological catalysts. If a catalyst is added that's in the same phase as the reactants, we call them homogeneous. If they're all gases, liquids, solids, aqueous, if all the adjectives in the equation are the same, they're termed homogeneous. If a catalyst is in a different phase as the reactants, some are gases, some are liquids, different adjectives if you will, they would be known as heterogeneous catalysts. The way a catalyst works is by altering the pathway. What it will do is actually provide a different set of collisions, a different mechanism, different sets of elementary reactions with the ultimate goal of lowering the activation energy. Thinking that through in terms of a diagram, if reactants form products, and this would be representing a single elementary reaction, there is a barrier called activation energy that separates reactants and products. If I can provide an alternate pathway that would lower the activation energy, we would then speed up the overall equation. What's important to note is that reactants to products, the overall change in the reactant product delta E or delta H for heat of reaction would be the same even if the pathway took to the top of the hill or just a different pathway with that catalyst. It doesn't change the overall energy of the equation, but it does lower the activation energy barrier. Let's take a look at an example that I've written. I have H2 plus ICl makes HI plus HCl. I'll call that step 1. Step 2, and these are elementary reactions. HI plus ICl gives me I2 plus HCl. If this are a proposed mechanism with two multi-step elementary reactions, let's write a balanced equation for the overall reaction. I can do that by simply adding together to find the overall equation, simplifying anything I can from the left to the right. What I notice is that HI is formed here and then made here. Something that's formed and then consumed in the next reaction is known as an intermediate. It does not appear in the overall equation. So here's what I'm noticing as the overall equation. I have H2 plus 2 molecules of ICl forming I2 and 2 molecules of HCl. The overall equation eliminated the intermediate HI. The rate laws for each elementary reaction would simply look like this. For the first elementary reaction, we would write rate is equal to K times the concentration of H2 to the first order times the concentration of ICl to the first order. The second elementary rate law would look like rate is equal to K, and this could be called K1 and K2 if this represents K1 and K2 for our elementary reactions, times the concentration of HI times the concentration of ICl. The intermediate appears in the elementary rate law. It does not appear in the overall equation. So we've written the rate laws for each elementary step. If the first step is slow and the second one is fast, what rate law do you expect to be observed? If the first step is slow and the second step is fast, what is the rate law we would expect to be observed? The rate law comes from the slowest step. The observed rate law would indeed match the first elementary reaction. If the first step is slow, it gives us directly our observed rate law. So rate is equal to K times the concentration of H2 times the concentration of ICl, first order with respect to both reactants, second order overall. When the first step is slow, that gives us directly the observed rate law. Now let's compare this to a second example I have written down below. Here we have a molecule of peroxide, H2O2, plus I negative, forming water, and IO negative. IO negative then reacts with H2O2, producing water, and I negative. We have some overall equations to consider. The overall equation is simply adding together both elementary reactions, simplifying what we can. What I'm noticing is a couple of interesting things. First of all, I have IO negative 1 formed and then used. IO negative 1 is what we called an intermediate. It's produced and then consumed. What I also see is that I negative appeared as a reactant and again as a product. I negative is a reactant in step 1 and appeared unchanged as a product at the end. This is known as a catalyst. Not a reactant, not a product. It simplifies out of the overall equation. It's something I added to alter the pathway to create a faster first step. The overall equation shows 2 units of H2O2 forming 2 molecules of water, and the rest has simplified out. I forgot to write O2. I'm not balanced. Sorry, I missed writing an oxygen in that second elementary step. I had to go back and add that. Peroxide breaks down to give water and oxygen. Oxygen O2, water, and I negative should have been written here in my example. Adding that back onto the overall equation produces a balanced equation for the decomposition of hydrogen peroxide. What it allowed me to do is to review what an intermediate is, something that's produced and then used, and the term catalyst, something I add and then get back at the end unchanged. The catalyst is I negative, the intermediate is IO negative 1. And if the first step is the slow step, comparatively to the second step, which we could say is faster, the observed rate law comes from the rate determining step. Rate is equal to K times the concentration of H2O2 and I negative. The catalyst appears in the observed rate law. It does not appear in the overall observed balanced equation.